People have always watched the shadows cast by the sun and noticed how the shadows move in the course of a day. Perhaps several thousand years ago, they thought of using the shadow's path to register the passing of time. It was in ancient Greece that people realized that the curves traced out by the end of the shadow vary, not just from day to day, but from week to week and from month to month. Sometimes we can see these curves marked on the surfaces of sundials. People realize that the curves are predictable from year to year. Interest grew in the kind of curves traced out by the path of the shadow. In the centre of Milton Keynes, this large sundial has the shadow's daily course marked on it. The real sundial is very shiny and it's hard to make out the lines, but this model of the Milton Keynes sundial shows them very clearly. The daily path traced out by the end of the shadow sometimes curves one way, sometimes the other, in what is called a hyperbola. Each day, a slightly different hyperbola is traced out. In fact, much the same thing happens all over the world. Pointing a torch beam at a wall will produce a cone of light. And where the cone intersects or meets a flat wall, the light produced traces out what we call a conic section. If the torch is pointed straight onto the wall, then that conic section is a circle. Tilting it slightly produces an ellipse. As it's tilted yet further, the ellipse becomes more and more elongated, until eventually the curve stops being a closed curve. At this point, the outer edge of the beam becomes parallel to the wall, and the outer curve is a parabola. As the beam is tilted even more, the arms of the curve spread out, giving a hyperbola. All these rather different curves, the circle, the ellipse, the parabola, and the hyperbola, come from the same experiment, from looking at the shape we get when a plane, like the wall, cuts a cone. So they are all members of a continuous family of curves. They are all conic sections. To end this part of the video, these conic sections are demonstrated on a physical model of the cone, on some historic film of one of the great mathematics teachers of this century, Bartel van der Waarden.
Here I have a cone. If we intersect this cone by a plane parallel to the base plane, then we get, as an intersection, a circle. You see, that's obvious. Now let's put it together again. But if we intersect the cone by a plane in a skew position like this, we get an ellipse. Now, I'm always astonished that this intersection has not the shape of an egg. It is just as large here at the bottom as on the top. This is an ellipse. But if we on the other hand, if we intersect the cone by a plane parallel to this tangential plane, then we get a curve which is called parabola.
this part of the video, we'll be exploring different representations of conic sections. They are the curves generated by slicing the cone by a plane. Let's concentrate on the conic section given by slicing the cone by a plane parallel to one of its sides. How might we represent this slice through a cone as an algebraic equation? We first need a coordinate system to relate things to. Often a property of a curve is so characteristic that it can be used as a definition. The parabola can be thought of as the set of points equidistant from a fixed point, the focus, and a fixed straight line, the directrix. Each point on the parabola is the same distance from the directrix, measured along the shortest way, which is the perpendicular to it, as it is from the focus. This is what characterizes the parabola. This relationship between the focus, the directrix, and the parabola is independent of any coordinate background. However, in practice, if we are to be able to talk about properties of the curve, we often need to refer to an underlying coordinate system. And to keep the equations relating the curve to the coordinate simple, it's often convenient to use the so-called standard position for the axes. The focus directrix definition we've got here is called a locus representation. The curve is the locus, or path, of points with such and such a property. In fact, almost any property will do. One such property might be to think of this parabola as the path of a point moving along in time, with its position given by a rule relating it to the underlying coordinate axes. All the different representations that we've seen for the parabola can be explored in much the same way for each of the other conic sections. For example, by looking at the ellipse as a slice of a cone, the ellipse has a focus directrix property. A point on an ellipse is always nearer to the focus than to its directrix in a ratio which is a constant for any particular ellipse. As for the parabola, the locus of such points can be taken as the basis for any defining representation. Ellipses can be represented parametrically, and the same pattern of different representations is also true for the hyperbola. These strong parallels between the different conic sections and their representations are what has led to their being called the family of conics.